Hello and welcome for this video which explains the concept of particular integral for higher order linear differential equations. My earlier video explains the concept of complementary function for when we start solving higher order linear differential equation with constant coefficients. From first order linear differential equations, we can recall the form dy by dx plus py equal to q, and the solution is obtained by this method which is mentioned here. Suppose if I consider a simple differential equation dy by dx plus ay equal to e to the power ax, I can obtain a solution. Thus e to the power ax by 2a plus c e to the power minus ax. Observation: when we solve a homogeneous differential equation, this part c e to the power minus ax turns out to be my complementary function. But in this equation, I'm getting one extra part e to the power ax upon 2a, which is because of the RHS. We can see RHS is e to the power ax, and same expression I'm having in this. If I try to relate the things with my polynomial f of t, e to the power ax by 2a can be written as e to the power ax upon a plus a, which turns out to be f of a. If I consider ft, I explained it in earlier video that fd is the polynomial which is representing my differential equation. So here my polynomial will be d plus a, where my d by dx is replaced by capital D. And this expression what we are finding here, 1 upon ft operated over e to the power ax, is the rules for finding particular integral. This y is equal to 1 upon ft, phi operated over my RHS is, I'm going to call particular integral. Why integral? Because capital D denotes derivative, and I'm taking 1 upon fd, that means as if I'm taking inverse of it. That means I'm trying to find an integral. That's why it is called as, particularly for phi x I'm working, that's why it is called as particular integral. Now it depends on phi x that how I can apply the rule. The example was explaining about exponential. So the rule one we are going to discuss is phi x when it is an exponential function. I'll directly state the rule here. If my f of a is not 0, then I can directly replace d by a, and I can just write my polynomial along with my exponential function. Suppose if it happens that f a is 0, that means I'm getting a case of failure. Then I'll check with f dash a. If f dash a is non-zero, then I can work with 1 upon f dash a. Now why this f of a we are getting is 0? This f of a will be 0 provided your e to the power ax is already a part of complementary function. If it is a part of complementary function, that means this is its another repetition. That's why to make it independent, I have to multiply it with x. So x into 1 upon f dash a e to the power ax. That is how I apply the rule. It may happen that e to the power ax already appeared in complementary function 2 times. Then I'll be getting fa as well as f dash a. Both are 0, but my f double dash a may not be 0. In that case, I'll multiply with x square and I'll use f double dash at a. And so on, I'll keep on working according to my complementary function. The concept is more understood with an example. So let us have a look at solved example. I have considered one second order differential equation here. Looking at the auxiliary equation, m square plus 4m minus 5 equal to 0. I'm getting real and distinct roots. The complementary function I can write as c1 e to the power minus 5x plus c2 e to the power x. Let us try to find particular integral, which is 1 upon ft operated over e to the power 5x. Now here my ft is d square plus 4d minus 5 and a turns out to be 5. If I substitute my 5 here, I'm getting 40, which is non-zero. So I can apply first line in the rule, that I can directly replace my d by 5 and I can write my particular integral to be 1 by 40 e to the power 5x. As a result, my final solution turns out to be y is equal to CF plus PI, which is the CF I have already found and PI I'm going to add to it. Let us have a look at a few more examples. I have kept the LHS same. RHS I am changing, e to the power x I have taken. So complementary function will remain same. Now here my a value becomes 1. If I substitute 1 in my FT, I am getting 0. That means it is case of failure. Why this is happening? Because e to the power x is already appearing in my complementary function and this is its second repetition. That's why I need to go with f dash d. When I work with f dash d, I'm getting a non-zero number. That means I can work with f dash d, I can substitute my a into f dash. So my rule is applied as multiply with x, divide by f dash and write the expression. And thus my final solution turns out to be y equal to CF plus PI, that is c1 e raised to minus 5x plus c2 e raised to x plus x upon 6 e to the power x. This was the first repetition, that's why the second repetition is coming along with x. More example to go. D minus 2 the whole square y equal to e to the power 2x. Now observe, I'm going to get 2 as my root here. That means 2 times it will be the root and RHS is also giving me the same expression. Auxiliary equation, real and repeated roots. Complementary function I can write c1 plus c2x e to the power 2x. That means I have already 2 times repeated e to the power 2x and this is its third repetition. So looking at the complementary function, here itself I can understand that f of a would be 0, will be case of failure. F dash a should also be a case of failure. So I may have to work with f double dash. This I can guess, I can see, I can observe from complementary function itself. Comparing complementary function with my RHS, I can do this. Look here, FD, f of 2 is 0, case of failure we are getting. F dash D, again we are getting case of failure. Why this is true? Because m equal to 2 is already repeated twice in my complementary function. F double dash D has to be non-zero and then I'll work with f double dash D, f double dash at 2, that is true. So my particular integral becomes x square by 2 e to the power 2x. Now look at the final answer. Final answer gives me e to the power 2x with c1, x e to the power 2x with c2, and that's why the third repetition will give me x square e to the power 2x just to make my functions independent. Few exercises.